Hello, I'm Brain Rainey, and welcome to my Oscillation Lab. Students will analyze the motion of a mass hanging from a spring and tracker. This mass will be oscillating horizontally and vertically. After creating experimental position versus time models for the x and y direction, students will create predictive position versus time models as well by altering a given GlowScript code. Students will then compare the experimental and prediction position versus time models. Students will also create a model of energy versus time that includes kinetic energy, gravitational potential energy, spring potential energy, and total energy through GlowScript. In order to accurately alter the code and properly analyze the results of this lab, students will need to understand multiple fundamental physics principles. The main principle used for this lab is the energy principle, which states that work is equal to change in energy plus Q. For this lab, students will choose the system to include the Earth, the mass, and the spring, so the work will equal zero as there's no change in distance of the total system. Because of this, the energy principle will simplify to this equation here. Two other principles utilized in this lab are Newton's second law, which is simply F net equals ma, and the momentum principle, which is used to derive the velocity update formula as seen here, and the position update formula as seen here. Here's a general video used for everyone, and you can see my tracker points of the center mass of the spring, and you can see it's going horizontally and vertically. Here are my results. These are the two comparison models of the object's position versus time, with the top being the y versus time and the bottom being x versus time. And the blue lines are the predicted values, whereas the red lines are the actual recorded values. And you can see they're both slightly off, but they're very similar, I would say. So I think it was a pretty good job. And the reason why they might be a little bit off is due to the iterative process of the prediction model and my tracker skills or lack thereof. And now to my data measurements and observations. Here is the model, which displays the object's position with a blue ball and the predicted position with the red ball. And you can see it's kind of lagging forward, jumping. It's very jumpy, and that's due to the iterative process. You can see this is the change in energy versus time graph, as shown here. And on the right is a created energy versus time graph, where the blue line is kinetic energy, the red is UG, the green is US, and the orange line is the total energy, which is zero, which I will talk about later. Here's the beginning of my coding. Based on the assumption that the object's mass and frame rate of the video lab are the same as the edX video, I was able to fill in these values the same as the edX video code. You can see here is my delta t, which is the same as the edX, and the ball's mass, which is the same as edX. I then updated the ball's initial position based off of my tracker data. Because we had a slightly different video, it had a slightly different initial position. I then calculated Ks through the formula as shown here and used this value to solve for L naught by setting the force of gravity equal to Fs, or the force of the spring when they're in equilibrium. That's how I solved for these two values, with the gravitational constant being the same. And I lastly filled in the generic spring and energy equations. You can see the generic spring ones and the general energy equations. Second part of my coding. Here I first updated the values of fgrav and fspring to create fnet, which just sums them together. Next I plugged in the velocity and position update formulas. I then copied and pasted the same spring and energy equations, and also added more general equations to the change in energies. As you can see here, I added like the delta energy is equal to the final energy minus the initial energy. And lastly, I made sure that the pos curve and pos2 curve plots were either both for pos x or pos y to create those two graphs that we saw earlier. What does it mean? You can see here that my model does satisfy the energy principle. And this is shown since the orange line is constantly equal to zero. And as I mentioned earlier, the work is equal to zero, and work is equal to change in energy. So the change in energy should be equal to zero, which it is. I found the period two different ways. One with the x versus time, and two with the y versus time. The one I actually used in the lab was y versus time, but I also created one for x versus time, which was actually 1.646 seconds. Meanwhile, my y period was 1.519 seconds. So this shows that based off of what you chose as your period of oscillation, your results would vary by, I don't know, roughly, what was that, 8% or so? Or maybe even 10%. It's roughly 10%. So that could be a decent amount. So thank you for watching my presentation.